Now let us go through these questions under linear algebra. Now the first question says, let V be equal to a two-dimensional real space. So that is V is equal to two-dimensional real space. Now what that means is you could well create any vector, or all the vectors which are under this vector space must always have components from the set of real numbers only in the x plane and the y plane. So if I picked out one vector under it, this might be 2 and we might have a minus 3 there. We could also have v2, and let's say here now we have a 3 and we have a 0. So that actually goes on and on because the real numbers, the set of real numbers are actually infinite. We cannot actually stop it. So you just need to know that every vector here would always be in two dimension. That is basically the meaning for the 2. That is, you will only have numbers in the x axis and the y axis. And that actually stops there. Now x and y, or any number which actually occupies x and y, must come from the set of real numbers. So that is basically the representation here. Hopefully by the time we're done with these questions, you should be able to understand a little bit under linear algebra, or hopefully more than a little bit. So we are required to show that W, which is represented by this definition, we have x comma y, such that 5x plus 2y is equal to a 10. Now, we mean that you could actually form vectors away from this set of vectors in such a way that the components of those vectors, if they were operated under this function or definition, you would always have 10 occurring or being formed. So let us say we have one vector under this. Let's say you have a 2, comma 0. If I took these numbers and operated them with this definition, if that gives me a 10, then we're going to say that this vector exists under this set. So let us try that. So this is going to be a 5 multiplied by 2. And here we're going to have a 2 multiplied by 0. Now here we know this is obviously going to give us a 10. So this is a 10 multiplied by 2 multiplied by 0. Well, this should be added. This is 10 plus 2 multiplied by 0, which is a 0. And so 10 plus 0 is obviously equal to 10. So this works. What that is going to say is that 2 comma 0, or W1, is actually a true vector or a member of this. So we could actually see W1 is a member of the set W. Now bear in mind, we have not actually begun answering this question. So this is just to build a basis or a premises for you to understand stuff. So I'm going to wipe these ones out. Now let us try another one. What if we chose out W2, and let's say that is equal to 1, and we got a 4. Would this be a true vector under this set? So let us try that. We have a 5, and that must multiply with the number which is under the x-axis, which in this case is a 1. And here we have a 2 multiplied by 4. So this is going to be a 5, and here we're going to have 2 multiplied by 4. So that gives us an 8. Now 5 plus 8 is obviously 13. 13 is not equal to 10. So what that means is 1 comma 4 is not a vector under this set. And so we're going to say that W is not a member or not an element under the set W. So we could well go on to find other vectors which actually exist under this space. Right now, I'm not actually going to call it a space. Let us just say this is a set. Just a set. Now we are required to find out whether or not it is subspace under a vector space. Now, it needs to fulfill three criteria. The first is that a zero vector must exist within it. So this is called the zero vector property. That is because for all vector spaces, you are always going to have that the zero vector will be a member of that space. And so every other set which vies to be a subspace of a vector space must always also contain the zero vector there. So a zero vector is represented this way. If we are going to write it in two dimensions, that is going to be a 0, 0. If we are going to write it in three dimensions, that is going to be a 0, 0, 0. Now, you could also have a zero vector in matrix form. That is called a zero vector or a null vector. This will be a 2 by 2 zero vector. And so continuously. But you need to know that the zero vectors must be contained in every subspace as well as a vector space. So if we do not really have a zero contained in this particular set, then that makes this set to fail from being a subspace under the vector space. But the question is, what if you find that a zero vector actually exists? What if it's going to be part? If it is part, then you need to go to the next test. And the next test is going to be called the closure under vector addition. What that means is picking out one vector and another and adding them. You should actually have that the answer should still exist under that subspace. And if you find out this works for that subspace, there would actually be a last test that you should work on it. So that will be the multiplication of a scalar with any vector chosen from that space. So let us say you have a u. If you have k multiplied by u, that still should be under that set. If you have this all fulfilled, then w, which is the set in that case, will be promoted to the subspace of the vector space. So hopefully you understand what I'm trying to say. Now let us try to check it. In this case, we're going to find out the zero vector property. So zero vector, that is going to be a 0, 0 in two dimensions. We say for a vector to be present or a part of this set, it must fulfill this operation. If you work this operation on all the values which are in that vector, that must add up to give a 10. If that doesn't work, then that vector chosen out is not a member of this. And it turns out to be, from face value, that this is not going to work. You're going to have a 5 multiplied by 0 plus 2 multiplied by 0. And should this give us a 10? Obviously not. You're going to have a 0 plus a 0. And this obviously will not be a 10. This doesn't work. So what that means is a zero vector is not a part of this particular set. And so we're not going to promote this set to a subspace. Hence, it fails. So that is actually the way to solve it. Hopefully you understand. And because we do not really have time, I'm just going to go on to the second question. And the second question says, write this as a linear combination of this and this. So I actually made a mistake here. I'm supposed to write out what that vector is. So W there should be this. That should be 0 minus 26 and 9. Okay? So we need to write this as a linear combination of those two vectors. So let us say W1 is equal to 5, 3, and 7. And let us say W2 is equal to 2 minus 4 and a 1. Now for linear combination, if you had stuff and you were required to tell what the linear combination of some vectors is, this is how you're going to write it. So let us say we got V here, and that will be A1 multiplied by V1, and that will be plus A2 multiplied by V2, and that actually continues until you reach A to the whichever number and V of whichever number. Now A, which I might well call now as AI, where I could stand for any position. 1, 2 continuously until you reach infinity. So this must be an element of the scalar field. That means any number under scalars or constants, you should have this as an element of it. And Vi, which is any vector which is chosen, must be an element of the vector space. So if you have that, then this representation is completely the representation for a linear combination. So we're going to use this definition and try to work it. So here we have that W must be equal to A1 of W1, and here we're going to have A2 W2. So what is W1? That is 5, 3, 7, and here we have an A2, and that is into W2, which is 2, negative 4, 1. And we need to FOIL these brackets using the constants. So W is going to be equal to 5 A1, 3 A1, 7 A1. And here we're going to have 2 A2, negative 4 A2. And here we're going to have A2. So that is actually what we have over there. Now, we need to add this stuff together. Now, first off, we know what W is. This is W. Because we do not really have so much space. Well, I think we do. So I'm just going to write it over here. So W is going to be the addition of these two vectors, this and this. So that will give us 5A1 plus 2A2. So that is going to be a 5A1 plus 2A2. And then you're going to have a 3A1 plus a negative 4A2. So that is going to be a 3A1. That will be a negative 4A2. And lastly, you actually have this plus this stuff. So that is 7A1 plus 7A1 plus A2. So that is what you have over there. And now we can actually bring out what W is. So we know that W is, okay. I think I could well combine it with this position. We already have this to be a W. And this is going to be equal to 5A1 plus 2A2. And here you have 3A1 minus 4A2. And this is 7A1 plus A2. Now we could actually combine this stuff together, or compare rather. So in this case we could say 0 is equal to this, negative 26 will be equal to this, and 9 will be equal to this one. So let us work that. So first off, we know that 0 is equal to 5A or 5A1 plus 2A2. And we know negative 26, that will be equal to 3A1 minus 4A2. And we know that 9 is going to be equal to 7A1 plus A2. Now we can solve this simultaneously. This is in order to find out what A1 as well as A2 is going to be. So how can we do it? And the best way to do this is to use the method of elimination. So I'm just going to use equation 3 and equation 1. Now, from here you can see that we have an A2 and a 2A2. So I could work elimination by multiplying this with 2. So let us do that. So let's say we have a 2 multiplied by this. So this is going to be a 9. This is equal to 7A1 plus A2. And this is what we have. So let's see what that's going to give. Here we're going to have an 18. And on these other side, we're going to have a 14A1 plus a 2A2. Now we also have a 2A2 on this side. So let us combine it. This is going to be a 0, and here we're going to have a 5A1, and here we have a 2A2. So if we subtracted this 2, we're going to have this to cancel out. And that will give us 18 minus 0 on the left hand side, which is going to be an 18. And here we have a 14 minus 5. That gives us a 9. So this is going to be a non-A1. So here we're going to see that A1 is going to be 18 divided by 9. And that will be 2. So therefore we have A1 is equal to 2. Now we're not yet done because we need to find A2. How can we find A2? That should actually come up very easy. If we took A2 and plugged it back within this first equation, that should give us a new number. So let us do that. This is going to be a 0. And here we have a 5 multiplied by A1, which is going to be a 2. And on this other side, we have 2A2. So this stuff is going to give us a 10. We need to take this to the other side, right? So this should be a negative 10. And this is equal to 2A2. So A2 is obviously going to be a negative 5. That will be the answer. Now we needed to write W as a linear combination of the vectors, the two vectors represented. So we're going to do that right now. So we know W1, that was equal to 2 minus 4 and a 1. And we had W2 to be, whoa, I made a mistake. So this should actually be a W2. Just going to write it there. And here we have a W1. So this is equal to 5. You have a 3 and you got a 7 there. So we know that this should be represented as this. We said W should be represented as A1, W2, or A1, W1. Just making a whole lot of mistakes. So this is going to be plus A2, W2. So let us try to do that. Now what is A1? A1 is 2 and W1 is 537. And we have A2. A2 is negative 5. So this would actually change. And this is going to give us a minus 5. And here we're going to have a W2, which is actually 2, negative 4, and a 1. So this is basically what you want to write. If you want to bring it out wholly, totally, that should be a 0 minus 26. You have a 9. And this is equal to 2 into 5, 3, and 7, minus 5, up 2, minus 4, and a 1. So that will be the answer to the question. This is what you're looking for. Now let us go on to the third one. That is going to be 2b. Now 2b says, show that this cannot be written as a linear combination of these two stuff. So let us try to do that. First off, for linear combination, there must be something like this. W should be equal to A1 W1 plus A2 W2, right? Now in this case, we're going to make W to be 1, 3, and 5. So we're designating that name for this vector. Now let us say you have W1 to be 5, 3, 7. Then we have W2. Let that be 2, -4, and a 1. So we actually need to have W. Okay, I've actually written that here, so I don't really need to write that anymore. So let us write it out. Now W, we know W is 1, 3, 5. This should be equal to A1 multiplied by W1, which is 5, 3, and a 7, plus A2 multiplied by W2, which is going to be 2 in -4 and a 1. I'll wipe these out. Now we need to FOIL these two brackets. So that is going to be a 5A1, 3A1, and a 7A1. So this is plus 2A2 minus 4A2, and we're going to have A2. That is A2 multiplied by 1, which is still going to give you an A2. Now next up, we need to add this whole stuff. So if you added this, you would form something like this, as usual. So this is going to be 5A1 plus 2A2. And this is going to be 3A1 minus 4A2. And you're going to have 7A1 plus A2. So that is what you have there. So in this case, we need to compare, right? So 1 will be equal to this, 3 is going to be equal to this, and 5 will be equal to this. So we can compare them now. I think I'm going to wipe out some stuff from here, as well as this. And so we have for the first equation, 1 is equal to 5A1 plus 2A2. We have 3 is equal to 3A1 minus 4A2. And the last one, we have a 5. And that is equal to 7A1 plus A2. So you're going to wipe these out. So we need to solve these systems of equations simultaneously. So let us start with this as well as this. That is equation 1 and equation 3. Now, if this is equation 3, we know we could use the elimination method and cancel out what is going to be A2. Now, we're just going to work with A1. So let us multiply this by 2. So that will be 2, multiplied by that. So this is 10. And this is equal to 14A1 plus 2A2. And we also have this stuff, so we're just going to combine it and work with elimination. So let us subtract that. This is clearly going to cancel out. And here you're going to have 10 minus 1, which gives us a 9. And on this side, we're going to have a 14 minus 5, which is still a 9a1. So that is going to make a1 to be 9 divided by 9, which is equal to 1. Now let us use a equal to 1 in equation 1. So that is going to be a 1, and this will be equal to 5 multiplied by 1, and this is plus 2a2, right? So this is going to be a 1, and here we're going to have a 5, and here we're going to have a 2a2, right? So if we took this 5 to the other side, we're going to have a 1 minus 5, and this is going to be equal to a 2a2. This is going to give us a minus 4, and then we'll have a 2a2, right? So we have a2 to be equal to minus 2. So that is what we have there. So in this case, we have answers for a1 and a2. Now remember, these were the system of equations we derived. We had the first 1 is equal to 5a1 plus 2a2. And for the second, we had 3 is equal to 3a1 minus 4a2. And for the third, we had 5. 5 is equal to 7a1 plus a2. So we're going to use these answers and plug all of them within each equation. If we have that the left hand side is equal to the right hand side, then that is actually going to work. So that would truly be that this vector is actually a linear combination. If it does not work for any of these equations, then that means that this is not a linear combination of the two vectors. So let us start with the first. This is going to be a 1. So we have 5 multiplied by a1, which is going to be a 5. And here we have a 2 multiplied by a2, which is a negative 2. So this is going to be a 5 minus 4. Clearly, 5 minus 4 is going to give us a 1. And 1 is equal to 1, so that works. Now let us move to the second. 3 is equal to 3 multiplied by a1. a1 is a 1. And here we have a minus 4 multiplied by a2. a2 is a negative 2. So this is going to be a 3. And 3 multiplied by 1 is a 3. Now if you had a negative 4 multiplied by a negative 2, that is going to give you plus 8. Now we know that 3 plus 8 should give us 11. And clearly here we see that 3 is not equal to 11. So this makes this equation to fail. So by that we can clearly say, therefore, that this form, this vector, is not a linear combination of these two other vectors. So that is basically what you need to do over there. Now here are some more questions. Number 3 says, determine which of the vectors are linearly independent. So we actually have two sets of them. This first and the second. So the first, you have the vectors 1, 0, 0, and you have a 1, 1, 0, and a 0. And you have a 1, 1, 1, and a 0. And the last vector is a 1, 1, 1, and a 1. So we need to find out whether or not these vectors are linearly independent. Now, how can you tell if vectors are linearly dependent? How would you know that? So let us say we have this linear combination. a1, v1 plus a2, v2 plus a3, v3. Continuously until you reach, let's say, am, vm. Let's say all these is equal to 0. Now, there is one condition. I should actually say there is actually many conditions But there will be actually one condition that will make these vectors to be linearly independent. If it is necessarily required that for the 0 to be formed on the other side, we must have a1, a2, a3 until you reach am to be equal to 0, then this is actually going to make all the vectors within this combination to be linearly independent. And that is actually pretty correct, right? If we have a1 to be a 0, this is going to become a 0. This is also going to become a 0 because we said that a1, a2, and a3 as well as am. Every other a's that you might well have in that combination. As far as you have them to be zeros, that obviously will create zeros in each case, right? And so if you added zeros together, that should give you 0. So we're trying to say if the necessary condition required for the 0 to be formed is that all the scalars or the coefficients in this case, which are going to be constants, if you always need to have them to be zeros, then that is going to make those vectors those vectors you're actually using these scalars to scale, those vectors are going to be called as linearly independent. Well, there could also be another form of this. You might not necessarily have the a's or the scalars to be equal to 0 for the 0 to occur. So if you have that being, let us say we provide a1 to be equal to 0, but a2, a3, and am are not equal to 0. This is going to cause the vectors to be linearly dependent. So linear dependence, so I'm just going to rewrite this. If you want to have linear dependence, that is going to be as a result of the fact that not all the scalars should be equal to 0. Here we're going to have a linear independence because we have all the scalars to be equal to 0. So this is going to be independence. Now we're going to work these questions using this analogy. So this is the first, this is the second, this is the third, and this is the fourth. So how can we work it? So we need to say, let us say this is the first vector. Let's say this is v1, this is v2. Let us say this is v3, and let this be v4. So if we have a1, v1, plus a2, v2, plus a3, v3, should make this v3, plus a4, v4, and all this equal to 0 in such a way that a1, a2, a3, and a4 must be equal to 0 for the zeros to occur, then we're actually going to say these vectors v1, v2, v3, as well as v4 are actually linearly independent. Because the only way that a 0 was to be formed is all the scalars or the constants here, they were actually required to be zeros. Now v1 is a 1, 0, 0, and a 0. And v2, that is 1, 1, 0, and a 0. Then we have a3 multiplied by v3. So v3 is 1, 1, 1, and a 0. Now what is a4? Well, v4 rather, that is 1, 1, 1, 1. Now all this must give 0. Now next up, we need to expand it. So let us try to do that. If we multiply the 1 into this vector, that will give us an a1 with a 0 and a 0 and a 0. And if we took a2 and multiplied it into this vector, we would have a2, a2, a 0, and a 0. And if we took a3 and multiplied it with this will give us an a3, 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 and a 0. And for this one, we're going to have a4s in 4 places. So this is going to be a4, this is an a4, and this is an a4. And all these must be equal to 0. Now, next up, we need to add these vectors. So if we were to add these vectors, if we added this, and with this, there is actually going to be some factors which should actually be gathered to one side. That is because this entry is actually only similar to the first entry of the other one and the first entry of the other, as well as the first entry of the last. So let me place a comma. So this should be a comma here. So this is what we're going to have. For the first, we're going to have a1 plus, so this will be a2 plus a3 plus a4, comma, and you have a 0 with an a2. That is, if you took 0 plus this, plus this, plus this, that will give you 0, a2, a3, and a4. So if you actually understand the pattern, and we could well create that real fast. So here we're going to have a 0 and a 0, and only an a3 and an a4 formed. And for the last case, we're going to have a 0 and a 0 and a 0, and finally an a4 formed. And all this is going to be equal to 0. Now bear in mind, this is actually 0 vector. So in this case, I'm just going to change it and make it to be this 0. So that is what you have. Even if you don't want to do it this way, that is pretty much still going to be the same thing. But I want to do this so that I could actually compare stuff. So from this comparison, we're going to have that a1 plus a2 plus a3 plus a4 will be equal to 0. Next up, we should have 0 plus a2 plus a3 plus a4. That is equal to a 0. And we have 0 plus 0 plus a3 plus a4 is equal to 0. And finally, we have a 0 plus a 0 plus a 0 plus a4 is equal to 0. Now, from this place, we could say that a4 is equal to 0 from the last equation. That is clear. Now, we're going to use a4 and plug it into this the third equation. So there should be 0 plus a 0 plus a3, and this will be plus a 0. Obviously, this is going to make a3 to be equal to 0. Now, going over to the second equation, if we took a3 and a4 and plugged it into this, we're actually going to have a 0 plus a 0 plus, there should be an a2 plus a 0 plus a 0. Obviously, you're going to have that a2 is also equal to 0. And by extension, we're going to have a1 to be equal to 0. So virtually all the scalars or constants are all equal to 0. Now, we said that if you had a1, a2, a3, and a4 equal to 0, and those vectors will be linearly independent. So as it is, we actually have that the vectors are linearly independent. So that is how to do it. Now you could well try to do the other one by yourself. Try to do this one. Now let us go over to the fourth question. The question says, let V be the vector space of polynomials with degrees less than or equal to 3. So we have something like this. And the polynomials f1, f2, and f3, oh, there is an f4. They form the basis of V. So if these are polynomials, f1, f2, f3, and f4, if they form a basis, then there must exist a vector which is actually going to be a linear combination of these other ones. Now bear in mind, functions could also be vectors. So that will be kind of like a linearly independent form. These are going to be vectors and they must be linearly independent. Okay? So if you have these linearly independent vectors added together by method of linear combination, that should give you that linear combination. So we're going to say U is a linear combination of these guys, where we say they are actually linearly independent vectors. So you should have something like this. I'm going to use a W multiplied by F1 plus an X multiplied by F2 plus a Y multiplied by F3, and we're going to have a Z multiplied by an F4. So we're just going to keep U as it is without plugging exactly the numerical values of it. Later on, we're going to do that. Right now, let us focus on the right hand side. So we have a W here, and F1 is actually a 1. And we have an X here. F2 is a T plus 2. And we have a Y. And F3 is actually a T plus 2 all squared. Then we have a Z, which is multiplied by T plus 2 to the third. So we actually need to expand some of the brackets on the right hand side. So this is going to be a U, and here we have a W, and we have an X. So what I'm going to do, I'm just going to leave it for now. So that will be T plus 2. And here we're going to have a Y. I need to open these brackets. So if you want to open them, that will be T plus 2 multiplied by T plus 2. If you did that, you should have T squared plus 4T plus 4. Now on this other side, I'm going to have a Z multiplied by T plus 2. And this will be multiplied by T squared plus 4T plus 4. And this is actually quite reasonable in it, because we should have T plus 2 raised to the third. That is the same thing as T plus 2 raised to the power of 2 multiplied by T plus 2. So this is what you have over here. Now this is what you have in the other side. So I'm just working it with substitution or implication. So we know that T squared is the same thing as this. Next up, I need to use this and FOIL this other bracket. So what is that going to give? Let us just work it real fast. So we have a T multiplied by this. That is going to give us a T cubed. And we have a T multiplied by 4T. That is going to give us a 4T squared. And we have a T multiplied by 4. So that will be a 4T. Next up, we're going to take it to and do the same thing with the other bracket. So that is 2 multiplied by 2T squared. That will be 2T squared. And you have a 2 multiplied by 4T. That is going to give us an 8T. And here we're going to have a T. Whoa, that should be a 2 multiplied by 4. That is going to give you an 8. So that is what you have there. Now we have T to the third left there. And here we have 4T squared plus 2T squared. That should give us a 6T squared. And here you have a 4T plus an 8T. That is going to give you a 12T. And lastly, we're going to have an 8. So that is actually the expansion of this stuff. So u will be equal to w plus x multiplied by t plus 2 plus y plus t squared plus 4t plus 4. And this will be plus z. That will be multiplied by t cubed plus 6t squared. And this will be plus 12t plus 8. So I'm just going to wipe this also. Now next up, we need to use this stuff and FOIL these brackets. So u is going to be equal to w plus xt. So this is xt plus 2x. And here we're going to have yt squared plus 4yt. And here we're going to have a 4y. And here we have a zt cubed. And we have a 6zt. That should be 6zt squared. And that will be plus 12zt. And plus 8z. So that is what you have. Now we could well add this stuff together, right? So how can we do that? In order to do this, we need to find out the forms which actually have the squares, and the ones which have the thirds, that is the power of 3, and the ones which just have just the first power, and the ones which are independent. So we just need to keep the left hand side the same because we do not really have space for that. So this is w plus, I'm going to start with the t raised to the power of 3. Happens to be that we just have one of it. So that is going to be zt, that should be zt cubed. Next up we have the t squared. So how many t squared do we have? We have this one and this one. So that is going to be plus yt squared plus 6zt squared. Next up, we need to work with the t's, the ones we just have the first power. So we have this, and we have this one. So that will be xt, and you have 4yt, and you have 12zt. And finally, we have the ones which do not carry a t. We have w, we have 2x, we have a 4y, and we have an 8z. So that is 4. So first we have a w, we have plus a 2x, and we have a 4y, and we have an 8z. Okay, so that is what we have over there. Now we could factor the ones which are in terms of a t squared and the ones which are in terms of a normal t. So I think I could wipe these out. So u is equal to zt cubed plus y plus 6z, and that is t squared, plus x plus a 4y plus a 12z. And this is multiplied by t. And the last one is pretty much just going to stay the way that it is. So this is going to be w plus 2x plus a 4y. So this is going to be plus 4y plus 8c. Now we know what u is. We were given u to be this stuff. So u is t raised to the power of 3 plus 5t plus 10. That will be equal to this whole stuff. So, well, I really don't want to write that, but I don't really got a choice. I'm just gonna write it out. This is t squared plus here we're gonna have x plus a 4y plus a 12z, and that is multiplied by t, and this is plus this stuff, which is a w plus a 2x plus a 4y plus an 8z. Okay, so now we can compare. We have stuff on the left hand side which carries some powers the same thing as the ones on the right hand side. So this is the left and this is the right. So concerning t raised to the power of 3, we have a z, whilst we have a 1 as a coefficient of t cubed on the left hand side. So here we're going to say that 1 is equal to z. This is actually very easy and great, because here we know that 1 is equal to z, or z is equal to 1, and that would really help us. So let us go to the second. It happens to be that we do not really have no t on this side containing the power of 2. So that will be a 0. And on the other side, we're going to have a y plus 6z, because we have a t squared here. Now we already know what a z is. So that is going to be a 0. And this will be a y plus a c multiplied by 1. So obviously we're going to have a 0, and that will be equal to y plus a 6. In order to find a y, we need to take the 6 to the other side. And so that is going to give us a negative 6. So here we know that y is equal to negative 6. This is also a beautiful one. And let us go on. Now comparing the ones in terms of the power of 1, that is going to be a 5, because on this side we have 5 as the coefficient of t. So that is going to be a 5. And here we also have stuff which carries the coefficient of t. This one. So we have that to be, need to write that in white. We have that to be x plus 4y plus a 12z. So we know what y is. We also know what z is. So that is going to be a 5. Here we're going to have an x. And this is 4 multiplied by negative 6 plus 12 multiplied by 1. So this is going to be a 5. And that is equal to x minus 24 plus 12. Minus 24 plus 12 is going to give us a minus 12. So that will be a 5. This is x minus 12. We could well take this negative 12 to the other side. And that will be 5 plus 12. And that is equal to an x. So here we can say that x is going to be equal to 17. Now finally, we're going to deal with the last stuff. And that is where we got a 10 on the left hand side. And 10 is equal to w plus 2x plus 4y plus 8z. We know that is z, that is equal to 1. Y is equal to negative 6 and x is equal to 17. So 10 would be w plus 2 multiplied by x, which is a 17, and we have plus 4y. Y in this case is a 6 and z is a 1. So you got a 10. And here you're going to have a 2 multiplied by 17, which is going to give you 34. And here we're going to have a 4 multiplied by negative 6, which is going to give you negative 24. And we have an 8 over here. If you have 34 minus 24, what is that going to give? That is going to give you a 10. So this is going to be a 10 plus an 8. So this is going to give us an 18. So we have 10 is equal to w plus 18. Now if you took 18 to the other side, that will be 10 minus 18. and this is equal to W. 10 minus 18 is going to give us negative 8. So that is a W. So in this case, we have actually found out all the coordinates, and we can now form the coordinate vector. All the values of the scalars that you have found, those are actually the coordinates. So we could say that the coordinates that is going to be 4. We're going to have a 1. I'm going to make it more chronological. So let us start with the x. We have 17. You have the y, that is negative 6. You have the z, that is the 1. And, well, I guess we're just going to write the w as the last. That is going to be a minus 8. Now, if we want to form the vector, that is a coordinate vector, that will be negative 8. You have a 1. You have a negative 6. And you have a 17. So that will be the answer to the question. That brings us to the end of this video.